still looking at people coming into the room, let me take the opportunity and welcome our speaker for today. Professor Tao Huan is an assistant professor at the Department of Chemistry at University of British Columbia in Vancouver in Canada from July 2018 to now. Before that, he was a postdoc at Scripps and La Jolla, 2015 to 2018. He earned his PhD at the University of Alberta in Canada on electrical chemistry and the Bachelor in Chemistry at Zhejiang University in China until 2010. He has an H index of 27, I-10 index of 45. I had the privilege myself to visit Professor Han and talk to his group not too long ago. And I must say, it's fantastic research they are doing. I enjoy their papers very much, and I clearly see Professor Tao Huan as one of the rising stars in metabolomics, and he's been also recognized by the Metabolomics Association of North America in the last conference. So welcome, Professor Tao Huan, and thank you so much for being here with us today. Professor Huan, the floor is yours.
Okay, thank you, Dr. Feng, for the very nice introduction. And it's also my great honor to present our work here today with a lot of metabolomics professionals and researchers. So today I'm going to talk about some big data challenges in processing mass spectrometry-based metabolomics. And as we all know, mass spectrometry is the most prominent analytical tool used for on-target profiling of metabolite. And especially when we combine mass spec with liquid chromatography, that further improves the number of metabolites that can be detected, and with a much better detection sensitivity and coverage. And here is the workflow of metabolomics study. We start from a sample preparation, we run our CMS analysis. Following that, we do a lot of data processing, and then goes into statistical analysis, identification, and finally, we move to the biological application. And as Dr. Feng introduced earlier, I am an analytical chemist. So what I am interested in is analytical chemistry and bioinformatics. Our goal is to make metabolomics more powerful, easier to use, and so that we can generate better metabolomics biological insight. However, at this stage, we have a sensitive mass spec. Those over $1 million sensitive instruments generate a large amount of data. On the other side, we have our biological collaborators waiting for us to send them the list of metabolites so that they can work from there. But we believe there is a big gap here, that is the bigger data challenges, because gigabytes of mass spec data generated. If there's any mistake in processing the data, it will completely distort the result and lead to some false discovery and waste of money and time. And our recent review paper on communication summarized these different topics of big data challenges that involved in metabolomics research. And in today's presentation, I'm going to introduce a few of our lab's research work to address these big data challenges to make metabolomics data easier to access. So the first thing is about the feature extraction. This is the first step after we get the mass spec raw data. We want to extract the metabolic feature from there. There are several well-established data processing software such as MS-DAL, XCMS Online, and MZMine, and now they have a version 3. But the bigger problem here is that there are so many parameters. Those here are the screenshot of I just did it this morning from MS-DAL. We can see your peak height, slice width, and also the advanced smoothing level, peak width, and also alignment, identification, and so many parameters to set. And how would a user know what is the best parameter combination for their LCMS data? To address this problem, so the question becomes how to find the best picking parameters. The conventional approach is design of experiment. Basically, we have a set of parameter combinations and we randomly try them one by one, and we have a output Y value, and until we get the best output, and we say, okay, that's the best parameters. So here are two representative work for this DOE-based approach, such as IPO and AutoTuner. However, the problem of design of experiment, personally, I don't like it, because when we deal with a problem using DOE, basically means that you treat the system as a black box. You don't know what happens inside. You just randomly try parameters to find the best. And also in metabolomics data processing, there are so many parameters to tune. And because of that, the DOE step can really be time consuming. So we try to think of this problem out of the box. Can we really directly measure the optimal parameters from the raw data without doing this tedious design of experiment workflow? We developed a bioinformatics pipeline called a Paramounter. The idea behind the Paramounter is that we come up with a list of universal parameters, and we directly measure these universal parameters from raw LCMS data. From there, we then convert these universal parameters to software-specific parameters and process the metabolomics data to generate the metabolomics feature table with the best performance. And to achieve this, there are several steps, and I would like to introduce them one by one in the following slides. So first is noise estimation. Noise estimation is trying to find which of those signals are contributed from noise and which are real metabolic feature. And we did it slightly different from what people do conventionally. So we do the noise estimation for each mass bin, and notably the mass bin is different from mass spectra. Mass bin is the extracted ion chromatogram of a particular M over Z value, as shown here, where you have x-axis retention time, y-axis intensity. Then you have the signal intensity at each of the retention time. Then we resort the intensities by their magnitude and from low to high. From there, we try to find a point where the signals on the right side, the mean value of signals on the right side is 3 times larger than the standard deviation of the signals on the left side. So this is basically adopt from the signal to noise ratio should be larger than 3 to determine a valid signal. And this allows us to get a mass bin specific noise level. Why that's important? Because conventionally, the way people estimate the noise level for their picking is to look into each mass spectrum. And then from there, they find, okay, the noise level. But notably, the noise level in the mass bins actually varies a lot, while the noise level in mass spectra are usually quite stable. So as we can see in the figure B here, we look at the mass spectra of different retention times there, and the y-axis basically is the noise level. We find the noise level is all around 2 to the 10 to the 3 for the QTOF instrument that we use in the lab. However, if you calculate noise level from the mass bin, where the x-axis is the M over Z value of that particular mass bin, we can find that the noise level is really M over Z value dependent. For some metabolic feature, there might be more background noise, so lead to higher noise intensity. Other M over Z values, those really high M over Z values, there's less background noise, so you will have a smaller noise intensity. In principle, when we identify the noise level, we are talking about the mass bin noise. But unfortunately, nowadays, when we do peak picking, when we input the noise level, most people will do the mass spectral noise, which is not a good representation of what noise is when we are doing the peak picking. Okay, so when we got to the noise level, the second thing is we try to identify those high quality metabolic features that represent real metabolites. In this case, we propose a concept called the zone of interest. So the left side basically shows how zone of interest looks like. We have an extracted ion chromatogram. In our previous slide, we already talked about how we can estimate the noise for this particular mass bin. We give a noise cut, and for the remaining data points that are above the noise level, we use the data point of the highest intensity as a reference. And then we use that as a reference to subtract the M over Z value of the others to get the mass difference distribution as shown on the bottom here. We believe that the real metabolic feature should have a relatively tight mass difference, while the noise level will have a really large mass difference. So from the mass difference, we can calculate the standard deviation to show the magnitude of the change of the mass difference. The beauty of doing this zoom of interest is that it is independent of the mass, the peak intensity. As we can show on the right side, for both a high intensity peak and a low intensity peak, as long as they pass the noise cutoff, their mass tolerance distribution will basically have a similar magnitude here. And then we can take the mass difference or the mass tolerance, and we can plot the distribution for all the metabolic features. Then we will get something on the left side here, where the x-axis is MOV value, y-axis is mass difference. It can be clearly see that most of the compounds that pass the noise level, they have their mass difference or the deviation that's relatively clustered towards the low value, while there will be a little bit, some of the features will be above, relatively high. So we can actually randomly pick some of those and take a look how their EIC looks like. For the features that have their ZOI mass difference below this, we cut off here. They usually have a relatively good peak shape. And then for the ones that above the threshold, they will have really bad peak shape. So from this result, it basically tells that we can use this mass difference distribution to find a cutoff and use that cutoff to represent the mass difference or mass deviation for the peak picking. And also, once we set up this mass cutoff, it allows us to capture those high quality ZOIs that are below this dashed red line. And using these high quality ZOIs, we can plot out the distribution of peak height, peak width, and mass retention shift, because we already know where they are. We know their MOV value, we know their retention time. And from these distributions, we will be able to find the best peak height parameter, peak width parameter, as well as the mass and the retention time shift for alignment analysis. And so with that, we will have all these mass tolerance, peak height, peak width, and instrumental shift ready as the universal parameters. And our software also incorporate a conversion algorithm, allowing us to convert these universal parameters to program-specific parameters. And of course, it's important to benchmarking against the other existing tool. So here, both AutoTuner and IPO, they have a benchmark data set in their paper, and we use the same data set and we process by parameter. And first, we can see that the number of features is significantly higher compared to AutoTuner and IPO. And in terms of running time, we are much shorter than IPO, but we are slightly higher than AutoTuner. But if you look closer into this, they are basically using a Google server. Okay, they are dealing with a Google server. And as a new research lab, we can't afford the cost. We only have a desktop PC to run this, so that it can be explained why we are slower than AutoTuner. But overall, I think our parameter approach allows us to really directly measure the optimized parameters from the raw LCMS data and the facilitator data processing. Of course, we also made other comparisons in the paper, but because of time limit, I'm going to skip those and you can read the paper for more details. So the next questions we always try to ask is, okay, now we have so many features detected. How many of them are real and how many of them are background noise? So, I mean, it's easy for us to manually tell, okay, these are good chromatographic peak shapes and these are bad chromatographic peak shapes. But how can we really manually check the thousands of features in the LCMS data? And that's really time consuming. And I did that when I was a graduate student about 10 years ago. It took me 5 days to finish one file. But now we are talking about hundreds of files for a metabolomic study. And how can we automate this? And my interpretation is that since we can manually tell the difference, there must be some pattern, although the pattern might not be easy for us to extract the variables, but we can use some computational tool. Here, we use a convolutional neural network to automatically learn the patterns of those high quality chromatographic peaks and the bad quality chromatographic peaks. And from there, we train the model, which is EVA, short for evaluation of chromatographic peak shapes. Here, you take the raw LCMS file, you process it by those data processing software, generate the feature table, and both the feature table and the raw data will be used as input for the EVA software because the model is being trained using 25,000 the EIC chromatogram, EIC spectra. And this is done during the COVID time where students have nowhere to go in the summer vacation. So I asked them to check a few thousand per student. So eventually we got a 25,000 manually check the data. And as we already said, right, it's not hard to tell if it's good or bad. So these 25,000 allowing us to get a really high quality model to predict the quality of the extracted features by these softwares. And there are multiple papers on the revision, and are gonna come out later showing how we can use this EVA approach to benchmark different softwares and also benchmark different data processing parameters. And we think this software is also important in the future for us to develop a better peak picking algorithms. Okay, following feature extraction, the next thing is quantitative comparison. In metabolomics, we usually do quantitative comparison to identify those statistically significant features. And one of the important steps is to calculate a fold change. And the way we usually calculate fold change is directly use mass spec intensity. So the question is, can we really trust the fold change calculated using mass spec signals in the linear ES range? Although this might sound not a problem because it's a linear ES range, then the mass spec signal fold change should be equal to the concentration fold change. But is that really the case? These are some of these overlooked challenges in metabolomics research. I think it's important to address them to get a high quality data set. So here is a linear relationship where the x-axis is concentration, y-axis is mass spec intensity. We have a metabolite in the sample 1 and sample 2. They have as you can see, the concentration fold change is about 2, right? So the sample 2 is about 2 times of the concentration of metabolite A in sample 1. But let's look at the mass spec intensity. The measured mass spec fold change is only 1.2. And that becomes a huge problem because when we do quantitative comparison, we usually have a fold change cutoff, 1.2, 1.5, or 2.0. So that being said, it's very likely that the metabolite is significantly different in 2 groups of samples. But just because you use mass spec signal to calculate the fold change, it can become non-significant. So that becomes, why would this happen? This is basically lead to the mathematical proportion versus the linear correlation. When we are talking about the proportion, y equal to kx and the intercept b is 0. In this case, y is the mass spec signal, x is the concentration. Okay, then you take the mass spec signal, you calculate the fold change equal to kx1 divided by kx2, cancel the k, then your signal fold change is equal to concentration fold change. But in metabolomics, we are most likely talking about linear correlation. Okay, y equals to kx plus b. Because of the existence of the b, your signal fold change will not equal to concentration fold change anymore, especially when the b value has a large magnitude, either it's very positive or very negative, then it will be very, very biased. And this can be easily tested by taking some chemical standards and run them in 2 different concentrations separately, one at 5 micromolar and another 2.5. Then you collect the mass spec signal intensity and you calculate the fold change. In this case, one is 5, another 2.5, so the expected fold change is 2. But when we look at the measured mass spec signal fold change, they're actually quite far away from 2.0. Some of 1.6, some can be 2.2. Then we can actually simplify this into a mathematical model to propose the 3 different types of ratios. One is compressed ratio. When the intercept b is larger than 0, your calculated signal fold change will always be smaller than the concentration fold change. And when the intercept is b equal to 0, then we are talking about proportion. Then the measured signal fold change will equal to the concentration fold change. Then no problem. On the other side, some cases the intercept b will be smaller than 0. Then your measured intensity fold change will be larger than concentration fold change. This is called inflation, ratio inflation, or fold change inflation. So these are 3 types of them. And this can also be validated using an on-target metabolomic study where we take a human urine sample, we dilute it into 10 different concentrations from 100% all the way to 10%. Then we run LCMS analysis of each samples individually. Then we compare their signal intensity. In this plot, the x-axis is concentration ratio. For example, a concentration ratio 10 is calculated by taking the 100% divided by the 10%. So the concentration ratio is the 10. Then because in the metabolomic study, we have hundreds of thousands of metabolic features, we can calculate the mass spec signal ratios for each one of the metabolic feature and plot their distribution in this violin plot. where this dashed red line represented the expected signal ratio. For example, a concentration ratio 10, we expect to also see a mass spec signal ratio equals to 10. But in reality, it's actually not. The majority of them will have the signal mass spec signal ratio below 10. Okay, so this is actually a big problem in metabolomics data processing, right? That the mass spec signal has a full change calculated directly from the analysis is actually not confident anymore. Okay, so then we need to come up with some solutions to correct the full change bias. I mean, this should be the many different ways, but we propose the approach by designing a serial diluted QC sample. So basically, you prepare the quality control sample, and you did either the serial dilution or you have different injection volume. From there, you can build this QC calibration curve for each metabolic feature, where the x-axis can be the injection volume or dilution factor, and y-axis is the intensity. And in real application, once you generate the metabolomics data for each metabolic signal feature, right? For the signal, you can map it into this QC calibration curve to get its corresponding injection volume. Then you calculate the injection. Then you calculate the full change directly using the injection volume or injection amount. In this case, because the injection volume is always proportion to the signal. In that case, your full change calculated using this injection volume or injection amount will give you a more accurate full change values. Next to this, another commonly used strategy called log transformation or power transformation. We've been using it for decades, trying to improve the data normality for better statistical outcome. But can we really trust those data transformation for improving data normality? Okay. The mechanism behind this is because we believe that metabolomics data are left skewed, so that when you apply the log transformation, it will bring the left skewed into a relatively more normal data, so that you can do a better statistical analysis. But is that the case? To understand this, we need to first understand the distribution of the metabolic features. So here we propose use a beta distribution to fit metabolomics data. So beta distribution will have two values, an alpha and a beta in this distribution algorithm. And by changing the alpha and beta value, it allows you to fit the metabolic features of different signal distribution. And so here what we do is we took a public available Alzheimer's disease data set, and it's a large data set with I think over a few hundred samples per group. And from there, for each metabolic feature, we can plot their distribution of relative intensities. And once you get the relative intensity distribution, you can plot fit the beta distribution and find the best alpha and beta value in this distribution algorithm to fit it. So in principle, there are all about 9 different combinations of alpha and beta representing 9 different types of data distribution. And we find that some of the data distribution are very rare. Like in this case, it's high in the low intensity and high in the high intensity, but very low in the medium intensity. This is very rare. But some of them are occasional, like that you will have high intensity, a few of them high intensity, but none of them are low intensity, or this type right skewed data. These are occasional, several hundred of features will have this type of data distribution. And on the other side, we do have left skewed and this type of distribution for most of the metabolic features. And those are more common data distribution. So we can think about when you have a left skewed data, right? And then you apply for the log transformation, it can solve the problem. But if you have a right skewed data, when you apply log transformation, it won't help. And how can we address the problem of those right skewed data? So here we copy the idea of box-Cox transformation, where the lambda is the tunable value. By tuning the lambda, you can find the optimal lambda value that converted whatever the original data distribution is to a normal distribution. So when we use because different features have different data distribution types, so we basically change the box-Cox distribution to adaptive box-Cox transformation, or with in short for ABC transformation. In this case, we can always find the best lambda value to turn this data into normal. On the other side, when we are talking about log or square root transformation, it only works for left skewed, but it doesn't work for right skewed data. And of course, we need to test its performance. We can mathematically simulate a data distribution, and then we can apply the different data normalization method, and then we check the normality after the data normalization. So here, if the original data distribution is already normal, then we don't have much issue. The normality rate after the transformation is always good. However, when we have right skewed data, we find that the original value has zero normality, but even if you do log and square root, it also has a very low normality rate. Only when you apply for the adaptive box cost transformation, it will allow us to bring up the data normality, which facilitates the downstream statistical analysis. On the other side, we realized that not all the left skewed data can be rescued by the log or square root. Only when the data distribution is in the log or normal form. On the other side, in a particular type of beta distribution, log or square root transformations actually will make the normality even worse. And this adaptive box cost transformation has also been applied to a real metabolomic study, which we identify several more significant changes in metabolite that are important to this biological question. And for more details, you can feel free to refer to that paper. Okay, the next thing is, as an analytical chemist, we also talk about analytical accuracy, precision, right? And we talk about how can we reduce the quantitative variations. So this is basically the equation I teach my second year undergrad study, where the total variance is basically sum of the analytical and the biological. And in order to improve data precision, we try to reduce the analytical variation as much as possible by better lab practice, by collecting the data on the same conditions and others. But in the omics level analytical studies, we rely a lot on computational tools to make data processing, to measure the quantitative values. So we propose that there's another quantitative variance here that can cause problem to the overall quantitative variation. And how can we really visualize this quantitative variation? So the way we can do is that we take a chemical standards, you run LCMS analysis, then you manually extract the peak height and the peak area shown in these blue dots. On the other side, you can use automatic data processing software to do the process. And each standard being analyzed 5 times, so you have 5 analytical replicates, so that you can calculate the relative standard deviation for each of the feature using both the manual approach and the automatic approach. And as we can visually see, our automatic approach by data processing software will always lead to a higher RSD compared to manual processing. And we can sum up all those metabolic values and put in the RSD distribution. In both cases, peak height and peak area, there is statistical significance between the manual picking and the automatic data picking. And we find that this problem the RSD can increase by 30% when using automated approach. And important to mention that here we are talking about chemical standards, but in real metabolomic study, there's a large, very big matrix effect, co-elution, and some metabolic features can have bad retention on the LC column. They have a poor chromatographic separation, and those can all further increase computational variation. Therefore, we think it's important that if we can come up with some solutions to correct those large computational variation, then we will be able to find more statistically significant metabolic features, and we will be able to find more biologically meaningful metabolites for downstream data processing. And this is still an ongoing effort because it's not easy to come up with a solution to really figure out which metabolic feature has a large computational variation. I hope the next time I see everyone, I'll be able to present some results that we have generated. Okay, so downstream, the quantitative comparison is about metabolite annotation. And because metabolites have a vast, diverse chemical structures, it's very difficult to accurately predict their MS structure. And also, we don't have that many standards to compared to the entire chemical space. In the end, when we are running metabolomics experiment, we always find some experimental MS spectra, but when we search against the database, we don't find the record there. And one common solution is to build in silico MS spectra that is to predict the MS spectra from a chemical structure. And when we are doing this, we usually will set some rules to guide the in silico prediction. Among them, a very important rule is even electron rule. Basically, we believe that even electron ions tend to form even electron fragment ions. And when we talk about LCMS analysis using electrospray ionization, right? And the ions are usually N plus H in positive mode or N minus H in negative mode. And those are even electron ions. And then the fragmentation is usually happening in collision-induced dissociation. That is a low energy. So we believe usually even electron precursor ions generate those even electron fragment ions. And the even electron rules are being heavily used to remove some predicted ions that are not following even electron rule. But is even electron rule really applicable to most of the cases, and how correct it is? So we did a study using the NIST 20 spectral library. So here, the way we tell whether it's even electron or other electron fragment ions is to check the non-integer double bond equivalent or DBE value of the chemical formula. So if we know the chemical formula, we know the molecular formula of the fragment, we can calculate the DBE value. And if DBE, and then this is basically what we did. We took the NIST 20 spectral library because this is well annotated. Each precursor and the fragment ions have their assigned molecular formula. And using this molecular formula, we can calculate DBE. If the DBE is integer, then it's a radical fragment ion, or it's an odd electron fragment ion. Otherwise, if it's a non-integer, then it is a even electron ion, or it's sometimes protonated ion or deprotonated ion, depending on whether it's positive mode and negative mode. So that's how we can check whether a fragment ion is a radical fragment ion. And using the well-established NIST 20, we studied all the hundreds of thousands of MS spectra, and these are structure disjointed, so they have a different chemical structures. And the result is actually surprising. Unlike what we believed, 99% of the ions should be even electron, we find that there's actually quite a lot of fragment ions are actually radical fragment ions. For some metabolites, in some MS spectra, it can add up to 50% of the fragment ions are radical fragment ions. So basically, the conclusion is that the radical fragment ions occurs more often in collision-induced based MS spectra than expected. And this basically raised a red flag when we are doing in silico fragmentation. We probably should not rule out those radical fragment ions. And of course, NIST 20 has all the chemical structure. We can use a classifier to classify all these molecules based on their class, superclass, and then we can calculate their radical fragment ion count and this is the percentage by count, and we also have a result of percentage by intensity. So from here, we can see that some molecules have a really high abundance of radical fragment ions, while others will have a relatively low. For example, for fatty acids, very low, and 1.2% radical fragment ions. And other molecules with those benzene ring, lots of conjugated double bond, it is more tolerable to these radical fragment ions. Basically, we find that the conjugated electron system help stabilize the radical fragment ions. So this study is basically provide some guidance for our future development of in silico fragmentation, and how can we make our prediction a real representative of the experiment outcome. Okay, so how we recognize the unknown metabolite, and this has been a really hot research topic with so many bioinformatics tools being developed over the past decades. And a common strategy is, and this is basically the introduction slide. People all know that when we do experimental LCMS analysis, a large majority of them are unknown. We search a database, we don't give the hit. And those are the metabolites probably that are not being archived in structured database, or they are just environmental pollutant that have not been studied before. A conventional way of doing this is to predict some chemical, try to predict its chemical structure. And the first step is to determines the molecular formula. And here is basically the work of Cirrus. For people who have used this, it's a very popular and well-established platform where you have the M of Z values, the precursor. You first search the database, you get all these possible candidates. And from the candidates, you can use a fragment tree approach to see if the candidate molecular formula can well explain the fragments. And we believe that the molecular formula that can explain most of the fragments in the MS2 spectra is more likely to be the correct formula. And these are being used in many different applications. However, Cirrus has a problem of first limited annotation accuracy and also high computation cost. For molecules with large M over Z values, you're gonna generate too many possible candidates, and then this calculation of the MS fragment tree gonna take a very long time. And usually people only do Cirrus for M over Z value under 500. Anything above that will take a very long time. So basically, we try to think out of the box, and we try to come up with this called a bottom-up MS interrogation. And this work has just recently been accepted in Nature Method, and you will probably see it in a few weeks. In our approach, we are not talking about first search the database to get a molecular formula. Instead, we use the rich chemical information in the MS spectra. The idea, the bottom-up idea, comes from proteomics, because in proteomics, people use the identities of each peptide to come up to the identity of the protein. And in the proteomics, bottom-up proteomics, the more fragments or more peptide information you have, the more confident the protein ID is. So here is the same thing. We want to implement that idea into metabolomics. So for each fragment, because we know the precursor M of Z value, so each fragment with a neutral loss. So fragment neutral loss pair. And the more fragments you have, the more fragment neutral loss pairs you have. Then we did an exhaustive search. We generate a formula database with over 3.5 million unique records. And these are from 26 different databases, including PapaChem and many others. So there are 26 different databases. Then for both fragment and neutral loss, they will all search against this 3.5 million records. So as you can imagine, in principle, right, the fragment will have a 3.5 million opportunity possibilities, and the neutral loss is also 3.5 million possibility. Then we combine the formula of fragment and the formula of neutral loss together, then that will lead to trillions of molecules. And notably, it's very important to realize that those trillions of molecules might exist in the database or might not exist in the database, because it's just a mathematical combination. So our approach, from bottom up by predicting the molecular formula of the fragment and neutral loss and assemble them together, really allows us to annotate those unknown molecules that are not in the database. Okay, then we're gonna do dereplication, because some of the combination might lead to the same molecular formula, and we also apply serious rules to get rid of some molecular formula that it's not likely to be true. For example, the too many oxygen, too little, too less and hydrogens, and those are follow the 7 golden rule that being established by Dr. Fink's group many years ago. And further to this, we will have the chemical space, right? Because each pair will generate a chemical space. Then all these chemical space basically will lead to a formula space that more likely to be the correct molecular formula is inside. Okay, from that, once we generate a formula space, we basically implement the MS1 information. Of course, this is optional, because sometimes we know the MS1 information, sometimes we don't. But it doesn't matter. Even if you don't have the MS1 information, if you don't have the isotope matching, we still implement the machine learned ranking. And this machine learned ranking is the model is trained using NIST 20 spectral database. As I mentioned previously, it's a well-established annotated database. And using that, we come up with about 20 MS1 features and about 20 MS fragment features, including the fragment DBE value, the fragment and others intensity values, and also their other information. Okay, so from this information, we can basically train this model and use the model to predict which of the molecular formula that's being synthesized in that step are likely to be the correct formula. And we also have a plateau calibration to assign a probability for each of the molecular formula. And the probability allows us to further calculate a false discovery rate. And the formula with a smaller false discovery rate is more likely to be true. Okay, so our work, implement many different things eventually to reach a accurate prediction of molecular formula. So first, I also want to mention about why we do this bottom-up approach. So think about the entire chemical space you have there, and for a certain M over Z value, when we directly search the database with mass tolerance, you're gonna lead to a lot of possible candidate hits, especially the mass tolerance is large. On the other side, when we are doing this mass explainable space, because we already only look for the ones that can be explained by the fragment and the mutual loss, and we can actually get a 20-fold decrease of candidate count. And that really allows us to deal with large molecules, because even if in the case of large molecules, we can still shrink down the candidate space and make it that computationally feasible to be processed on a personal computer. And of course, benchmarking is important. We compared our tool named Buddy against the Cirrus using this mass bank of Helic, and those are well-established database with the annotated molecular formula information. So then we can really tell if it's correct or not. So top one accuracy here. Buddy always can achieve around 90% the top one accuracy, and it's usually considered much better than the Cirrus here. Here we are talking about the large scale 24,000 structure disjoint MS spectrum. And we didn't really stop there, because we really want to make a comprehensive bioinformatics solution for people to address the dark matter. And how can we link, some of them is annotated, by the structure identification by chemical standards, and others are molecular formula annotated by Buddy, right? How can we link them? And here we incorporate the idea of the global peak optimization or global peak annotation. Basically, we believe that for the metabolites that's in the biological samples, many of them would have some kind of a feature-to-feature relationship, either through a biotransformation reaction or through others. So to achieve this, we implement a global optimization, and this idea was initially come out from Joshua Robilski's lab in Princeton. They had a paper a few years ago about global peak optimization, and we incorporated this idea to facilitate the molecular formula annotation. And the goal is to refine the molecular annotation of the individual features, and it also allows us to review the possible biotransformations between the known and unknown metabolites. So here's one example. We took the urine sample we processed by MS dial. We get about 6,000 features. Among them, half of them have MS2 and half of them don't have MS2. Then by comparing chemical standards and the reference MS spectra, we identified 213 as we showed here. This is molecular networking analysis. The red dots are the ones that have been confirmed. We have a 6,000 dark matter that's not been confirmed. Then we perform the bottom-up MS interrogation. We can get 92% of them annotated. Okay, there's a molecular formula there. Then a step further, using this global peak annotation or global feature optimization, we can actually link about 5,000 of them to these identified metabolites. And our work basically offered alternative solution to the existing molecular networking analysis and others to help address this dark matter. We find that near 85% of features can be structurally annotated directly or indirectly. Directly means that those are identified, and indirectly means those are linked to the identified metabolites. And due to the time limit, I'm not going to, there are actually a lot more other examples in the paper that people can refer to. And one thing I want to really point out, we have a very good graphic user interface, and everything is freely available. All the data sets, all the testing data sets, all the library, and everything is freely available on GitHub. And basically, this you can input either a single MS spectra, or you can input an entire metabolomic study. And we have a specific unit that can directly take the metabolomics data outcome from MS dial. So you can directly input the MS dial output, and then basically you will have all this feature information listed here, because in the MS dial output, you have the MS information there. So we can directly come up there and you press the compute, right? And then we'll run everything. I will show you the molecular formula, and we also will show you which database that this formula is presented. So as you can see, these are a few examples. We have a toxin database, endogenous metabolite database, and also natural product database as well. And then here, and also help you to explain the MS1, MS2 data, and hope that people can give a try and let us know if there's any problem. We'll be happy to help you to work together to get the software better. Okay, with that, I think I'm on time. And finally, I would like to thank most of the work being done by my first 3 graduate students, Jian, Shipei, and Huashi. They are all about to graduate this year, especially for this body work. Basically, Shipei spent 2 years, learning from how to do this thing and how to do programming and coding and all these things. And also thank you all for the funding agents. And finally, thank you for your attention, and happy to take your questions.
Great, thank you so much. That was a wonderful talk. Really explained all the nuances and issues that we face in metabolomics big data sets, and really broke down all of the solutions that you've been working on in your lab. There are several questions in the chat, so I'll just get started. You first explained the difference between noise in bins versus a chromatogram, for example. So going back to that topic, how does noise differ between different instruments, for example, a QTOF and an Orbitrap? And how does the noise differ over chromatograms when you're specifically thinking about positive versus negative ESI?
So the definition of noise actually, there's not a well definition, because noise, it depends on what application you're talking about. It can refer to the mass spec signal noise, or sometimes called dark noise being generated in those instruments. And sometimes the noise can also be those features, metabolic features contributing from the contamination, the system contamination, or from, I'm not sure, Dr. Finn's question is about this noise bin here.
Not specifically to the bin, but just like
Sure.
the noise that's different between instruments.
Right. So in general, I think noise is poorly defined, and it really depends on the circumstance people are talking about. So here, when we're talking about noise, we are more talking about the analytical dark noise, where just the signal pops up for no reasons. But of course, when we are talking about this type of analysis, right, and those are also noise, right? Those could be noise, and also yeah. So my lab only have a QTOF, so we haven't really made a comparison between QTOF and Orbitrap. Definitely between positive and negative mode, at least in my experience, we find the positive mode ESI is have more noise compared to negative mode ESI.
Interesting. Why do you have a inkling to knowing why that might be the case, like why in positive more?
Yeah, I thought about that before. I was thinking maybe we are talking about the salt and also other contaminants. They are more likely to be nitrogen containing, and those are easy to be ionized in positive mode.
Yeah.
On the other side, the negative mode, usually we feel it's relatively clean. But haven't really systematically studied or investigate this problem.
Yeah, people don't really publish or talk about noise so much, but it is an important factor when you're thinking about data and in metabolomics data in general. So the next topic that you had covered was fold change, which was really interesting because I hadn't realized those differences. So one of my own questions was, before using the fold change correction that you had mentioned, in general, what is more accurate in terms of the fold change that you described, the concentration fold change or the mass spec fold change, since there was such a big difference and we do use a cutoff like you were mentioning. That was kind of interesting to see how big of a difference you can find.
Right. So basically, from our study, I think it's we believe that the mass spec signal fold change is definitely not accurate. And then I talked to some of my colleagues, they said, oh, what they will do is they will not look at the fold change, they only look at the p-value.
Okay,
Yeah, so that's a possible solution.
interesting. Okay. And then sticking to the same topic there, for comparison of fold changes, were all adducts from each compound taken into consideration? Also, have you noticed inconsistencies between methods, as compounds may not experience the same ion suppression on different LC methods, for example?
Yeah. Sorry, can you repeat your question again? I want to try to catch the point.
So for comparison of the fold changes, were all adduct formations taken into consideration? And then did you notice differences in fold changes when you use different methods?
Here we didn't add up all the different adduct forms, so we only here look at the M plus H. And because this is a chemical standard solution, so we think the distribution of different adduct, their intensity distribution should relatively stable. But you definitely mentioned the point that it's really depend on method, depend on LC gradient. This is just something that's it's not a constant. Say for example, keto-glutaric acid. You know, in this case, it would be 1.6. But then if you switch to a reverse phase column, you switch to mobile phase, it might be a different fold change. But at least the fold change is not 2.0, okay, not the real fold change.
Okay, great. And now moving on to the next topic on distribution. Do you see differences in data distributions between real metabolites, for example, annotated compounds, and other features that might not be true metabolites, for example?
That's a very good point. We didn't look into that. In the study that we did here, it's all about metabolic features, but I think I'll definitely ask the students to take a look of the mass distribution between real metabolites versus putative metabolic feature or background noise. I think there must be something behind this. And we hypothesize the reason why you have this type of different distribution mainly contribute from the two factors. One is the nonlinear ESI response. Another is the inherited biological distribution. Some metabolites might have a skewed biological distribution, and then you overlap that on the top of nonlinear ESI response. So to make the feature intensity distribution really unpredictable. But yeah, I think that's a good idea to take a look at the real metabolites and metabolic features. Yeah, very good point.
Yeah, because they could be, you know, saying different things, and it's definitely would be helpful to the community at large to kind of understand those differences, especially when there's like, you know, people starting out new in metabolomics and they might not understand the true differences.
Another outcome from this analysis is if metabolites really have different distribution than metabolic feature, then we can build a machine learning model, you know, to tell based on the distribution whether it's a real metabolite, more likely to be a real metabolite, or more likely to be a background noise. That can be another layer of a filter.
Yeah, that's true. The following topic that you discussed was variance. There's a question here on that. What is the actual cause of computational variance? Peak picking, baseline fitting to be easier in a manual way than in an automatic way? Which parameters, software were used for automatic peak picking, etc.?
Right. So the main problem as shown on this slide is that some of the metabolites, they have a bad chromatographic peak shapes, causing from either low intensity or just their poor chemical interaction with the stationary phase. Because that the peak shape is not ideal Gaussian, it will, you know, have a little bit of zigzag here, and that sometimes will fool the peak picking algorithm when they are trying to determine the peak area or peak height. And our results find out actually peak height based determination is usually more accurate compared to peak area based determination. Because nowadays when we have those high quality LC columns, the reproducibility of the peak shape between the different injections usually very good. Okay, because of that, the peak height determination usually is easier compared to peak area, because peak area will find it difficult to find where the peak starts, where the peak ends. So
Okay.
that is where the problem happens, computational variation.
Okay, that's good to know.
So also another thing I didn't mention here because we have a manuscript in preparation is the alignment issue. There are a lot of the misalignment. Even the data set is analyzed on the same day. There's no large retention time drift, no systematic retention time drift. There is still chance of misalignment. And the misalignment will basically also cause a large RSD because you are aligning different features together, and those two will have a large variation.
Okay. Yeah, so kind of there's the next question here is kind of going back to fold change, but it talks about the importance of, or asks the importance of using internal standards. So how would internal standards-based normalization perform in representing the biological fold changes compared to your approach? Of course, you know, internal standards, they might be limited in numbers, but it is a good approach in terms of normalization.
Yeah, totally. I think both the stable isotope internal standards, or those people call chemical isotope internal standard, where you label the metabolite by a chemical tag, and the chemical tag can be stable isotope labeled. Both approach can address this fold change bias. Definitely, yeah. But we don't have the data to support that yet. I think but that could be pretty straightforward, and we can give a try. But definitely using internal standard will help. That also means that in the future, when we find some metabolites are really critical to the biological story, probably we need to use this internal standard to get their accurate fold change, especially for those pair of metabolites that involve in a metabolism reaction. ADP, ATP, GH, GSSG, right? So in order to correctly capture the ratio to refer to the biological outcome, probably you need to spec internal standards.
Okay, great. And now kind of going on to the topic of compound ID with your tool that you mentioned, Buddy, which is very interesting, and I definitely will be testing it out. There's a question and comment here. I understand Buddy is biased towards existing chemicals through matching to 23 databases. These databases include PubChem, which has far more small molecules than large molecules, or larger molecules that are driven by lipids, but not exactly large polyphenols. How do you address that?
Right, so that's why we have 26 databases. So it's not only about the PubChem, we also have a lipid database, natural product database. Basically, we spend continuously about half a year to find all the possible databases we can find that's public available. Drug database, everything. And also, the Buddy here is only for metabolomics, which we deal with the small molecules. So definitely, if there's actually we wrote that in the research briefing on Nature Method. It's definitely will have a problem if a certain class of compound is not there, especially in the machine learning training part. So training here based on NIST 20, right? So if there is a certain class of compound that's underrepresented in the NIST 20, then the model that we trained will have a bias, towards that. Those are all the issues we realized for machine learning. But at least so far, we trying to capture as many chemicals as possible and do the machine learning. We use the most comprehensive, well-annotated database. And in the future, definitely, if there's more available data, we can retrain the model to make it more robust.
Yeah, I noticed that it was only in version 1.3, so I imagine there's plenty of new ideas and new versions going to come out in the future. Yeah. So sticking to Buddy, if 10% of the features in the data set can be annotated and essentially 90% is dark matter, what proportion of dark matter is real but unknown? And what proportion is just, I guess, unknown just random features or just unimportant features? Right.
So this slide here, the 80% is just a rough number. So we can take a look here. So when we say total peaks here, we already did some round of filters there. For example, we filter out those low abundant features of signal intensity below certain threshold, and also we basically add several other filters to get rid of those low quality features. And even doing that, we find the majority of them can be chemically annotated. But of course, chemically annotated not necessarily mean that it's metabolized from the biological system. It could contribute from your sample preparation or other things. But at least the buddy approach allows to do this annotation and get more chemicals that's annotated.
Great. There's a question here still on the buddy topic. Is the metabolite network in buddy any way or shape form related to GNPS and what GNPS does in terms of networking?
We don't have a molecular networking here. So
okay.
When we are talking about networking, we are talking about the connection by biotransformation reaction. It's different from GNPS. GNPS is about the spectral similarity, so it's a different concept.
Okay, great. Thanks for clarifying that. A few more questions here. What was the data set, was the data set the same that was used in the machine learning? And if students cross-check between each other's peaks, if cross-checked, it would be interesting to look at the bias between different users, i.e. what different people call a peak. This would further help to elucidate what's the cause of error is between computational and manual approach. It may be hard to say that manual is a gold standard. So it's a little unclear in terms of the question, what data set they were referring to. But I guess, like the overall topic of the question here is, when you're comparing like machine learning for, I guess, peak picking and, a manual approach, just your eye and, you're looking at the peak, what's going to be the differences there?
I think this is related to validation, and the way we did the validation is using those reference library, because in this reference library, each MS spectra has a molecular formula. So these are the ground truth. So basically, we basically tested software in these ground truths to achieve the over 90% top one accuracy. So basically, that's what we demonstrated the performance here.
Oh, I do have clarification on the question here. It was more specifically towards asking the difference between the manual versus computational error, not for MSMS. So
right.
Yeah.
About, I think it's somewhere this one, computational variation here. Right. So sorry, what's the question again?
So was the data set the same that was used in the machine learning, and if the student cross-checks between each other's peaks?
Here it doesn't involve machine learning. We just use MS style to process the data, and we checked the student did the manual checking why MS style sometimes lead to higher RSD. It's mainly the problem where you have a chromatography peak shape, but somehow the starting point is here, the end point is here. So that's how it was integrated. And the good thing about MS style, we like it, is that if you notice these things happen, you can click into it, you can manually select the new cursor for it to recalculate the integration. And that's what my students think is really helpful. But at least if you don't close your eye, you just rely on the software to do the automatic peak integration, then there might be problems.
Gotcha. Okay. So moving on to another question, going back to Buddy. By using Buddy, does it also reveal in-source fragments, unexpected adducts, dimers, for example? What were your observed percentages of those hidden in the unknowns?
Sure, yeah, no, but Buddy here is mainly focused on molecular formula prediction, and in terms of in-source fragmentation and different adducts form, we have other softwares. ISFrag, which was published last year on analytical chemistry, that can help do that. But for this series, for this Buddy work, we didn't investigate how many of these annotated contributed from in-source fragment, but that can be easily checked using the other softwares to do it.
Yeah, and especially in your data processing pipeline, for example, MS Style, you can definitely check for in-source fragments and
Right.
kind of either, you know, track them or include them and kind of keep an eye on that. So there's just one last question here, kind of like a general, you know, big picture question coming off of your talk. So your talk highlighted a lot of ways that metabolomics analysis can be improved. You know, there are several things that you had mentioned about the noise that we see, fold change, distribution, etc. How dramatically do you think the conclusion from biological studies that utilizes metabolomics would change if all of your highlighted issues were addressed?
Sure.
Big question.
Yeah, definitely. I think this can be approached from several different aspects. One is I always believe, back in we always talk about the biomarker discovery, and we said about this biomarker discovery have a low accuracy. People have been trying this for decades, but there are very few cases, successful cases where metabolomics guided the biomarker discovery. So my personal feeling is that the reason why we have a low success rate because we haven't fixed those quantitative issues. So we haven't fixed these big data problems, because in proteomics, genomics, they don't have the problems that we are facing in metabolomics. So by solving these problems, we can definitely make the metabolomics data quality much higher and make them more likely to have the success biological story. On the other side, I also want to emphasize that no matter what we do in metabolomics, we basically just present a list of candidates. It's still lead to the biologist to validate them in the biological experiment. That being said, you have a feature with maybe 100-fold change, with a p-value 1 × 10 to the -10, but it doesn't pass the biological validation, then it is still meaningless compared to other metabolites. Maybe have a relatively high p-value, 0.04, for example. But yeah, it passed the biological validation, then that's important. So that leads to the fact I think it's important when we are doing metabolomics, we try to capture as many features as possible and using our data processing pipeline to extract those high quality features. And then it's lead to biological experiment to make the decision which one is important. Yeah, so overall, I mean, on our side as analytical chemists, we always try to improve the data quality, but whether the higher quality data quality necessarily lead to the more biological discovery, it's really depends on the biological system itself, right? If the biological system don't really have any significance there, then no matter how good your machine is, how sensitive your instrument is, it's not going to lead to any meaningful discovery. So yeah, so we are doing our work.
Yeah, that's a very good point. I mean, we could have the most expensive, most, top-notch instrument on the tool on the market, but at the end of the day, if the biology there isn't clearly present, there's only so much we can do. But you also bring a really good point that the biological interpretation is also quite difficult. It's not just the compound identification process, and that's can cause a bottleneck. So yeah, with that, if there aren't any more questions, I would like to thank you for a wonderful presentation. It's been great hearing your talk again. I really enjoyed your talk in Canada earlier, or last year, and so this was really good to hear again. With that, I'd like to thank everybody for joining. I would like to talk about our next speaker next month. So we have Dr. Mariam Ghadarzi joining us to talk about the impact of fast food on the gut microbiome and host metabolome. Dr. Ghadarzi is a core leader and a board of the Metabolomics Association of North America, also known as MANA. She's now currently the treasurer, so definitely will be excited to hear from her on what she has to say about the gut microbiome and fast food. I'm sure there's I'm sure we all enjoy a little bit of fast food every now and then. So with that, I hope you guys can join us in February. Till then, I'll see you next time.